Good afternoon, everybody. Today we're going to have a bit of a discussion around the conventional and unconventional cost perspective on comminution circuit design. It's a project that FLS has been working on for quite a while in terms of how we really look at utilizing our equipment and bringing a new perspective into the future of mining and really focusing this specific study on comminution circuit design. We start off with a challenge that I think our industry is facing, and it's something that's a bit of a slow burner at this point in time. We need to talk about our declining head grades and really what it means for our industry. Over time, I think in the past we were talking about 1% copper grades going into a concentrator. At the moment, there's most and many concentrators are looking at 0.25%, so 0.25% copper head grade feeding into their plants. And what does that really mean for us in the bigger scheme of things? If you look at the bottom right there, to scale, we have in the middle, so if we look over here, that really is a 1% copper ore. And to scale, your little bit of copper in there is going to be 1% of the total value. Now, what declining head grades means for us ultimately is we still have to produce the same amount of copper. That copper demand is not going to go down, but the amount of material that we have to process will then actually have to increase. So it's not about less with the same. We really have to produce the same with more copper. So part of what we're looking at is how do we take this, and what does this actually mean? So if we just take that example over there, if we want to produce a 1 ton of copper, ultimately that means we need to produce and process 400 tons of material. And if we compare that to, let's say, a 1% copper grade, that means we're going to be putting 399 odd tons of material onto a tailings facility. What does that get us in the other side of it? So there's the quid and the pro, the quid pro quo. We can produce around 12 EVs with 1 ton of copper. We can get around 5 American homes, that's 200 kilograms per home of copper, about 40,000 cell phones, or we can get about 2,000 laptops. So really that gives us a little bit of perspective of what our 400 tons of tailings really gets us, right? So ultimately, what does this really mean for us, and particularly around the comminution circuit, is how can we as FLS, as an organization, really take this forward and say, how do we help our industry? So obviously, if we take a bit of a sporting analogy, and we can always say supersize everything. And this is what we've done over the last number of years as we produce bigger equipment, bigger mills, bigger crushers. And then we go to the point where we're physically limited with what we can achieve, and then we start installing multiple units of our equipment, right? So we do 2 gyratory crushers instead of 1 gyratory crusher. Unfortunately, I don't know if that necessarily is going to be a sustainable model. Higher capex is going to be an issue with this, and obviously when we take that further, our emissions associated with the manufacture and production of steel is going to be a challenge. What are our alternatives? Well, we can say, put me in, coach. What can we do here? We can use alternative technologies. In this case, what we looked at over with our study that I'm going to show you in a second is using an ERC, which is an eccentric roll crusher, instead of a gyratory crusher, right? Again, there are some benefits to that, and we'll have a quick word about what we've done there. But that's also not necessarily solving the problem. It's more of a marginal increase. Expanding the roster, looking at technologies that are beyond what we traditionally consider as part of a copper concentrator. And I'm referring mostly to copper concentrators in this example, but it's still applicable to other commodities such as iron ore and the sort. So we could do sorting, where we say, hang on, we're still going to process our rock, but we're just going to sort out the crap rock before we make it smaller. And that's a complementary technology that we will work with industry to try and see if we can make an improvement there. And then really the final option that we have in principle is to change the game. how do we change and challenge the conventional way of thinking and the conventional processing technologies to find a better way of doing it. And I think one of the most appealing technologies that we've got at this point in time is the concept of the coarse flotation. So taking our grind size from something like 150 micron, which is a typical copper concentrator, and seeing if we can do flotation at something that's a little bit more coarse at, let's say, 350 micron. And that's kind of a paradigm shift in the bigger scheme of things, because our whole industry is rigged around flotation at 150 micron. Our whole industry is rigged around separation and classification at up to 350 micron, if you talk about the workhorse of a cyclone. So that's really things that we need to look at in the future. So we had a customer case where we had a traditional customer. They came to us and they said, let's go and see what we can do. What is in it for us in the bigger scheme of things? How can we have a view of this and take a different view? So we compared two conventional circuits, a primary gyratory crusher SABC circuit with and as well as a HPGR ball mill circuit. We had a look at that grinding to 150 micron, and then we said, well, what can we do if we do an unconventional grind at 350 micron? So we incorporated two technologies there, or two flow sheets, a wet and a dry circuit, where we took an ERC and we added an FTM at the end, a tower mill at the end. And then we also looked at an HPGR-based dry finish grinding circuit, where we take the HPGR product to 150 or 350 microns. That study is still in progress, so we're not really going to focus on that a little bit more, but we'll have a look at what we got with the ERC solution and what we did there. So just in the bottom left there, we decided to build ourselves a conceptual 100,000 ton a day copper concentrator and see what came out of this. So what was our approach? How did we start developing this, and how did we go about this study of ours? Basically, we started late in 2023 and into 2024 with collecting of our samples. So we got a fairly significant, shall we say, sample donation from a mine, a copper concentrator. As we said, their head grade is sitting at 0.2%, so kind of really a real-world application. We then took that material, tested it through our materials testing and research center in Salt Lake City and various other places. So we also had some testing that was done in Germany on the HPGRs, and basically that gives us that material testing leg that we did there. From there, we designed a 100,000 ton a day copper concentrator. We did those two circuits as we described, and then to really take it to that next step and the next level, we partnered up with Wood PLC to develop a full PFS level evaluation of this. So it's not just then a question of its FLS trying to sell the equipment. It's really looking at what does this mean overall to our end users, and say what is the actual cost of that. And just for specific reference here, if you look at those numbers, and we know, because we know who it is, obviously, but this is an exceptionally hard ore. Within the ores that we deal with, this is probably in the top 10% of hard material. So it is a very difficult ore to process. As we went along, we developed these two to challenge the conventional. There, we looked at the conventional circuit, which is obviously, as we said there, it's a primary gyratory crusher. It runs into three ball mills, or three sag mills, apologies, and going into three ball mills, and those are fairly hefty, biggest of what we've got pieces of equipment. We compared that to a circuit which contains an ERC as the primary crusher, your conventional cone crushers as your secondary crushers, going into 4 HPGRs, and then eventually into 10 tower mills. We needed the 10 tower mills to be able to get us the capacity, but it still turned out to be a significant number of equipment to do that. Our final outcomes, one of the big things that I just wanted to highlight here is really looking at something like the ERC as a technology, as an alternative technology to the primary gyratory crusher. When we look at it from a design point of view and an installation point of view, it really is a very promising technology for us. It's a very unique technology. It's a very unique crusher. But the real benefits there for us in terms of your owner is that your installation cost and your associated capex with that piece of equipment is significantly reduced because your earthworks is dramatically reduced over what a primary gyratory crusher would need to be. It really is very much in a sweet spot between some of the technologies, the performance technology or performance parameters of a jaw crusher, but at the scale of a gyratory crusher. So we are very, very excited by this. This was baked into the study, and there were some significant cost savings that we achieved with that. Now, when we look at the oh, cracky, I think I went too far. When we look at the overall energy savings, this was quite interesting for us. Typically, as we would have expected, the SAG mill versus HPGR circuits, there was quite a big savings there. 25% of the total instantaneous energy reduction just by going from a SAG mill to an HPGR ball circuit. And then with our alternative HPGR FTM circuit, grinding to 350 microns, there was an additional 22 odd megawatts of power savings that we could introduce into that circuit. Obviously, depending on the downstream flotation circuit being able to process and separate at 350 microns. Typically, as we would have expected, the SAG ball mill combination had a very, very high power contribution, and then that is kind of traded off against what we do with the HPGR eventually. When we look at the overall capital costs, surprisingly enough, the HPGR circuit as a baseline was actually cheaper than the projected cost of the SAG ball circuit, which is going a little bit against conventional wisdom at this point in time. But really what's happening there is the capital cost of your ball mill, SAG mill combination at that incredibly hard material really drives the overall cost of your circuit, of your grinding circuit. Unfortunately for us, to some extent, the not so good news was that the FTM circuit didn't give us the financial savings that we were looking for, and we believe that that's really partly due to the fact that we still need to optimize that circuit and really button it down from a development point of view, make sure that we're optimizing the circuit design and getting the correct infrastructure associated with the FTM circuit. But it was promising nonetheless. We also then had a look at the overall operating cost, where we looked at not only the wares and spares cost over the life of, or on a yearly basis for the three options. Obviously, there's a bit of a trade-off when we're doing a SAG mill versus your conventional milling and even the FTM, where grinding media on a SAG mill is going to be your primary operating cost. Whereas against an HPGR, you're going to be converting some of that into wear parts, so the rollers, etc., etc. But there was still quite a significant contribution overall in terms of grinding media to the study, and then obviously the natural effect of power came out of the equation. What is important here again, it's not only about the instantaneous, it is also about the power savings that we can generate out of grinding to a coarser product. So the last example there gave us an additional saving of around about $20 million a year of operating costs that we could potentially save and pass on to our customers. Over the life of the mine, this is where it really, where the rubber hits the road. Obviously for FLS, we sell the equipment, but our customers have to live with this for the life of the mine. And really, again, there in this really hard rock application, it's quite clear that the sag mill combination for this really hard rock is going to prove to be an expensive option for the life of the mine. So some of those savings that we sometimes see when we're designing these circuits might not necessarily come to fruition. We did see that the trade-off in terms of the capital cost of our FTM option that we did as the unconventional, that does bear fruit in the long term. So there is a little bit of a discussion there around trading off capital in the beginning and saving that over the life of the mine. In terms of our key takeaways, really, grind size is not only it's something that we really need to target. I think there is, as a holistic approach, obviously our novel and unconventional grinding technologies, that's where we can offer some savings and we can certainly challenge the norms there. But ultimately, this is a holistic thing, and FLS as a full flow sheet supplier is also looking into this, at how we're going to achieve these grind size benefits. As I said earlier, the high capacity hard rock processing plants, we might not necessarily see sag mills being deployed into that. It really requires us to work together with our customers and make sure that really is their best circuit. HPGR is now finally starting to get to the point where, as a new technology, it's starting to be accepted into industry 20 years later, that we've now been able to port it out of cement and really prove and validate that this is an alternative. There are new alternatives on the market, so things like the FTM, things like the ERC are certainly technologies that we see in that very exciting phase that our previous speaker spoke about, where we're excited to see the development coming our way. And they really do provide compelling alternatives to the flow sheet. So really, declining head grades, it's a problem, it's a challenge, it's something that our industry is going to have to face to make the demands of industry and the globe around things like copper and our critical minerals. A comment here that somebody made to me previously, where he said, the best flow sheet might not be your best flow sheet, and it might not be our best flow sheet. And I really think that this is an opportunity for FLS as an organization to have these types of discussions and say, not only is it about the equipment, but it's about what it means to you in the long term, and how we can partner and make sure that we provide value to our customers. And that's it. We enable conventional, unconventional technologies that are efficient and sustainable flow sheets. So thank you. I don't know if there's any questions. Are we doing questions? No questions. Fantastic.